Hi Year 8, this is our fourth lesson for our topic of Pythagoras' Theorem. In this video we're going to look at irrational numbers. So far in this topic we've learnt how to write Pythagoras' Theorem and then how to use it to find the length of the hypotenuse or the length of the shorter side. And then we also looked at some practical applications. So a rational number is one that can be written as a fraction, but more formally we say it can be written in the form p over q. P and Q have to be integers. They're whole numbers, remember? And Q, the denominator, can't be equal to 0. So let's have a look at some of the numbers that are rational. So, for example, whole numbers are rational. How do we write a number like 5 as a fraction? 5 over 1. So it's rational. Fractions obviously are rational, even mixed fractions like this one. Let's turn this into improper. Do you remember how to do it? 3 times 1 is 3, plus 2 is 5. It's 5/3. So fractions are also rational. Terminating decimals are rational. Do you remember what terminating means? It means to stop. So like 0.7. How do we write 0.7 as a fraction? 7 over 10. There we go, it's rational. And recurring decimals are also rational numbers. Recurring means it repeats, and they go on forever and ever, like 0.3 repeater. We can write it like that with the dot over the 3, that means the 3 continues on, or we could write 0.3333 dot dot dot. Either way though, this one is actually equal to 1/3, and all recurring decimals can be written as fractions. And then finally percentages are also rational numbers. How do we write 47% as a fraction? 47 over 100. Now an irrational number cannot be written as a fraction. They are non-terminating, non-recurring decimals. That means they don't stop and they never repeat. Now arguably the most famous irrational number is pi, and you've probably heard of pi. It starts 3.141592653, etc., etc. It goes on forever. We're going to study pi in more detail later in Year 8. If you want to have a look at it on the calculator, then you need to find this button here. And it's just sitting above it. So we need to do Shift, then press that button, then press equals. And we will get the first 9 decimal places of pi. Now curiously, it's been rounded. Have a look. 3.141592653. Do you see how it's been rounded? Because the next decimal place is a 5. So if we are going to approximate pi, we have to use the approximately equals to symbol, which is these two wavy lines. Or you can use an equal sign with a dot above and a dot below. Another famous irrational number is E, or Euler's number. It's sometimes called the natural number as well. On the calculator, you'll find it above this button here, which looks like in, but it's actually LN. So it's just sitting above it. So you've got to go Shift, then press that button, and you actually have to put in e to the power of 1. So you'll have to use your arrows to navigate up into that power position and put a 1 in. And this is what you'll get. So it's another irrational number. It doesn't stop, and it doesn't ever repeat. And other irrational numbers include surds. A surd is the square root of a number that is not a perfect square. So for example, square root of 2 and square root of 3 are surds, and they're both irrational numbers. So you can see how 2 and 3 are not perfect squares. Do you remember the perfect squares? They're 1 squared, 2 squared, 3 squared, 4 squared, etc. So 1, 4, 9, 16. 2 and 3 are not perfect squares. And if you put them into the calculator, you're going to get a non-repeating, non-terminating decimal. They're irrational. So root 2 is approximately equal to 1.414213562. And root 3 is approximately equal to 1.7320508088. Square root of 4 is not a surd. Why? Because 4 is a perfect square. So remember, the square root means some number times by itself gives us 4. And that's 2, isn't it? So square root of 4 is 2. And we can write 2 as a fraction, 2 over 1, which makes it a rational number. So I thought you might be curious to look at the set of all real numbers. and that's this here, and it's given the symbol R. It's got a funny looking double line here when we write this R. So that stands for real numbers. These are all the numbers that you're going to encounter all the way up to year 12. Now within that set we have the rational numbers, and it's got the symbol Q. And it's got the symbol Q because it stands for quotient. And remember how we said that rational numbers can be written in the form P over Q? So they can be written as a quotient. Outside here, these are the irrational numbers, and we do Q with a little dash after it, and this means not Q. So let's have a look at all of these numbers and see where they fit. Let's start with this percentage up here. Percentages are rational, so they go in the rational number set. Fractions are rational, so they go in there too. E is irrational, and so is pi. The square root of 2 is a third, so it's irrational. Now be careful with this one. Square root of 9 is actually 3, because 9 is a perfect square. And 3 can be written as a fraction, can't it? 3 over 1, so it's rational. All recurring decimals, like 0.3 repeater, can be written as fractions, so they are rational. Square root of 11 is irrational, it's a third. Terminating decimals like 0.7 are rational. Whole numbers like 110 are also rational. And I've thrown this one just in to trick you. The square root of -1 doesn't actually exist, it's not real, so it goes outside this set. Now the reason that I'm telling you all of this is because sometimes when we do a question for Pythagoras' theorem, it asks us to leave our answer as an exact value rather than approximating it. That means leave your answer as a third. So this particular question, when we do our working out, we're not going to get a nice answer, a nice whole number. We're going to get the square root of something. When we put it in the calculator, we'll get lots of decimals. So basically, this is actually easier than what I've been teaching you because you can stop one step earlier. I'll show you what I mean. We're going to start by writing Pythagoras' theorem. X squared is equal to 7 squared plus 10 squared. 7 squared is 49, 10 squared is 100. And add that up. Now we'll take the square root of both sides. X is equal to the square root of 149, which is not a nice number, and that's where we stop. We don't have to write approximately equal to and then work out the square root on the calculator. Okay, that's an exact value, and it is a third. Let's try one more. Find the value of y, leaving your answer as a third. Now this one's a short side question. Can you see that? But we're still going to start the same way. 17 squared equals y squared plus 9 squared. Now let's work these out. This is 289 is equal to y squared plus 81. And then subtracting 81 from both sides, we're going to get y squared is equal to 208. Finally, let's get rid of this square. Do the square root of both sides. Y is equal to the square root of 208, and that's where we're going to leave it. Okay, so that's it for this video. In our last video for this topic, we're going to look at theoretical applications of Pythagoras' theorem.